All right, class, welcome. In the world of power electronics, we all start out learning about the ideal diode, right? That perfect one-way street for current. But today, we're going to peel back that simple model and uncover the two very real and sometimes clashing personalities that every single power electronics designer has to master.
You see these things everywhere, from the charger for your phone to massive industrial motor drives. But here's the thing, you can't let that simple schematic symbol fool you. Hiding inside is a really complex behavior that makes the difference between a great design and a very expensive failure.
So, here's our game plan. We'll start with a quick review, then we'll look at the diode's static portrait. After that, we'll crank up the speed to see what happens, get into the details of reverse recovery, and then put it all together.
Okay, let's jump right in. We'll start at the beginning. What do we all think we know about how a diode works? At its most basic level, we've got this PN junction. It's designed to be a one-way gate, a one-way street. Current flows from the anode to the cathode, no problem. But if it tries to go the other way, the gate just slams shut. Or does it?
So that brings us to the first face of the diode. We're talking about its static behavior, how it acts when things are nice and steady under DC conditions. Now, look at this. On the left, that's the diode you learned about in your first circuits class, a perfect, clean on-off switch. But on the right, well, that's the real world. It's this messy, nonlinear curve. And that curve isn't some kind of flaw. It's the diode's true signature, and we have to understand it.
Let's zoom in on this curve. We can really break it down into three distinct areas. You've got your forward biased region, that's when it's on and conducting current. Then the reverse biased region, where it's supposed to be off and blocking everything. And then you have this cliff, the breakdown region. This is the danger zone. You push a diode in here and it's game over.
And believe it or not, there's a beautiful piece of physics that describes this entire curve perfectly. It's called the Shockley diode equation.
Now, I know an equation like this can look a little scary, but don't focus on memorizing it. Look at the pieces. Things like IS, the reverse saturation current, and VT, the thermal voltage. These aren't just abstract variables. They are the fundamental properties of the device itself. It's like the diode's genetic code, telling us exactly how it's going to behave.
And here's where it gets really cool. In the forward direction, that exponential term just completely takes over. It's like opening a fire hydrant. A small turn gives you this massive exponential gush of current. But when you go in reverse, that exponential term basically becomes zero, and all you're left with is that tiny, tiny leakage current, negative IS. It's like a pipe that has a very, very small constant drip.
Okay, so we've got a handle on the static diode. It's predictable, it follows the math, but modern power electronics don't live in a static world. We are switching these things on and off millions of times a second. And that's where we meet the diode's other, much more complicated face.
So that VI curve we just looked at, that's for a diode that's just sitting there taking its time. But what happens when we tell it to go from fully conducting to fully off? In, say, a few nanoseconds, what does it actually do?
Well, it turns out it can't just snap off. The problem is, when it's on, the junction is flooded with charged carriers. And when you try to turn it off, those carriers don't just disappear into thin air. It's kind of like a wet sponge. Even after you wring it out, there's still some water left inside. That leftover stored charge is the root of a huge issue called reverse recovery.
And this is it. This is the second face of the power diode. It's dynamic reality during the turn-off process. If you are designing anything that switches fast, and these days, that's everything, you absolutely have to understand this.
Okay, take a good look at this waveform. This tells the whole story. We command the diode to turn off right here, but look what the current does. It doesn't just go to zero, it actually shoots negative. It conducts in reverse for a short period of time before it finally gets its act together and turns off. That whole event, that is the signature of reverse recovery.
We can actually break this little event into two phases. The first part, called TA, is basically the time it takes to sweep out all that leftover charge we talked about. The second part, TB, is when the junction itself actually recovers and remembers how to block voltage again. And if you add TA and TB together, you get the total reverse recovery time, or TRR.
So as an engineer, how do you quantify this? You go to the datasheet and you look for two critical numbers. First is TRR, the recovery time. How long does this whole mess take? The second is QRR, the recovery charge. That's the total amount of charge that got pulled out backwards, and it's literally the area under this part of the curve.
And here's another critical point. Not all diodes recover the same way. What you want is a soft recovery, where the current smoothly and gently returns to zero. What you absolutely do not want is this, an abrupt or snappy recovery. When that current snaps off instantly, it's like slamming on the brakes in your car. It induces massive voltage spikes that can, and will, destroy other components in your circuit.
This all leads to one of the classic, fundamental trade-offs in all of power electronics. If you look at the math, you'll see that if you try to switch the diode off faster, that's a high DI/dt, you do get a shorter recovery time, which sounds great, right? Less time wasted means higher efficiency. But the price you pay is that your peak reverse current, IRR, goes way up. You're putting way more stress on the device to gain that speed.
Okay, so let's bring this all together. What's the big takeaway here? It's simple. You cannot be a good designer by only understanding one side of the story. You have to master both of these personalities, the static one and the dynamic one.
And this slide really says it all, doesn't it? On the left, you have the static portrait, that nice, clean, predictable VI curve for when things are stable. And on the right, you have the dynamic reality, that messy, complicated, and dangerous reverse recovery waveform that shows up every single time you switch. They're two faces of the exact same component.
So why do we care so much about this? Because if you ignore this dynamic behavior, your circuit will fail. You'll get huge unexpected power losses that cook your board. You'll generate a ton of electromagnetic noise, or EMI, that messes with everything around it. You will literally break components, and you'll never be able to push your switching frequencies high enough for a modern design.
So it really comes down to this. High-performance design isn't just about picking parts from a catalog. It's about knowing these components inside and out, both their steady-state behavior and how they act under the extreme pressure of high-speed switching. That's how you build things that are efficient, reliable, and powerful.
So I'll leave you with this thought. The next time you're in the lab and you grab a power diode for your design, I want you to stop for a second and think about this. How are you going to account for both of its faces? Because learning to answer that question, well, that's what's going to make you a great power electronics engineer.